So good morning, students. So you all do one thing, you just repeatedly listen the class so that you can get the idea. In today's class, electrostatics, we are going to discuss about linear charge density, surface charge density, volume charge density, and charge is quantized. Quantized. Charge is quantized. Let me finish this one first. Charge is quantized means charge Q is not a single electron. It is equals to number of electrons or number of charges. Either it may be plus or minus. Minus means negatively charged particles. Plus means positively charged particles. Charge is quantized. Suppose you are taking this one, conductor, and which includes some electrons in this 3, 4, 5, 6. What is the charge of this conductor? Charge of this conductor is Q, denoted with letter Q, and is equals to not one electron, because a small charged particle of charge is 10 to the power of 1.6 into 10 to the power of minus 19 Coulomb. This is okay, but it includes second one, third one, number of charges. How many number of charges? That number you need to write here. That number you need to write here. Suppose here there are 6. 6 into 1.6 into 10 to the power of minus 19. Or nothing is given to you. Then you can write here n. Number of electrons. Number of electrons. This is called a charge is a quantized. Charge is a quantized. One more point. Charge is invariant. Charge does not go any change due to its motion. This charge will not change when it is moved from here to here. From here to here will not change. 1.6 into 10 to the power of minus 19 Coulomb remains. Suppose a object is moving like that, it may acquire some kinetic energy, it will acquire some potential energy. But here we are talking about charge of electron, charge of this one particle. This charge will not change. 1.6 will remain even if it is traveling longer distances, moving from one place to another place. Every time inside the conductor, they are neutral like this. If suppose some excess charges are there, that will be located on the surface of, that is, charge is located on the surfaces. Suppose this rod is a extended rod, I mean length, only along one dimension. The charge over this surface, not surface, in its length, along the length, charge is distributed along the length of the conductor. Then lambda is the linear charge density and is like this, q by L. Charge per length is called linear charge density. Come on to the surface. Suppose I am taking a sheet and the charge is spread over this sheet. And one more thing I will tell here. At the sharp edges, suppose this sheet is like this. Here is the sharp edge. Here the charge is located. Charge is located in a maximum quantity at the edges and the corners, on the sharp edges. And this sigma is defined as, surface charge density is defined as charge per the surface. Surface charge density is given to you like this. The charge is spread over the surface or surface area. You can write like this: surface area, that is sigma is equal to q by a, aerial charge density or surface charge density. So when one example I will tell, this where you are using at a building, you will have a bar, long and sharp edged bar at one end of the building. So this is the setup over the building because here at a thunderstorm, when lightning occurs, this charge will be received by this one. Since it is connected to the earth, and you are getting positive charge here, then immediately the negative charge over the sharp edge will get attract this thunder, so that this total electrical current or thunderstorm getting into this one, it may be melt, so that the building cannot damage. It will works on the principle of surface charge density. Charge density. Repeatedly listen the same statement. Surface charge density. Okay. Lightning rods used on the tall buildings to prevent lightning from the striking the building. We'll work on this one. Surface charge density, linear charge density, surface charge density, and then come on to the volume charge density. This is the rho. This is the charge density. For this one, if the charge is spread inside the spherical sphere, metallic sphere, conductor only, then volume charge density is equals to charge per unit volume. And here I will draw one more to get idea about surface charge density. Suppose sphere is like this, and additional charge is spread over the external surface of the sphere. This will come under surface charge density, not volume charge density, right? And this sheet also, inside this sheet, I mean this one. Suppose it is a charge is inside this one. It is not surface charge density, it is a volume charge density. External one, this one. Okay? Listen this one carefully, once again and once again. Now, write the formulas for this. Charge is quantized, that is Q is equal to N, and linear charge density lambda is equal to Q by L, and surface charge density sigma is equal to Q by surface area, and rho is the volume charge density Q by volume. Unit of this one, unit of Coulomb per meter, and this is Coulomb per meter square. How easy it is. Coulomb per meter cube, and Q is equal to number of electrons. It is only Coulomb. Unit of this one is a Coulomb. And in today's class, we came to know about linear charge density, surface charge density, and volume charge density, and the charge is quantized, and the 4 formulas. Suppose this is okay for here. If this area is changing, suppose the sphere is circular shape is given, your area formula is pi r square. Square sheet is given, your area formula is breadth square or length square. If rectangular is given, then your area will be length into breadth square. Volume also will change. If it is a cube, no problem with that. You will get a length into breadth into height. Suppose it is a sphere, you will get a 4 by 3 pi r cube. Volume is 4 by 3 pi r cube. Okay. Note these formulas. Okay. So in the first day class, we came to discuss, already we discussed about Coulomb's inverse square law statements only. That is, F proportional to product of two charges, and F inversely proportional to square of the distance between them. So now you came to know what are the charges, how the charge is distributed over the surfaces and inside the object, and the distance is this one. This may not valid for, I told you already, some limitations are there for Coulomb's inverse square law. This is valid only for point sized charges, not for large. Okay, and now I'm going to derive the formula for this. F is equals to 1 by 4 pi epsilon 1 by 4 pi epsilon naught into q1 q2 by r square. This is your formula. This is your formula for Coulomb's Coulombic force between charges. Either it may be attractive forces or repulsive forces. You all know that there is attractive force between one positive charge and one negative charge, and there is a repulsive force between two similar charges. Okay, so this is the formula. F is equal to 1 by 4 by epsilon naught into q1 q2 by r square. What is epsilon naught? Permittivity of free space. What is the permittivity? Sambhavyata. When you are keeping two charges in air, when you are keeping two charges in air, sometimes you are keeping these two charges in oil, and you are keeping these two charges in water, air, and oil. Then the magnitude of force between these two, Q1 and Q2, and Q1 and Q2, same charges, is placed in a three mediums. Three mediums. When you are keeping these three pair of two charges in three mediums, the force will vary. The force will vary. The same force of attraction between these two charges or repulsive force between these two charges will not occur. This will change according to medium. That information, how much the change will get, will give you from permittivity symbol. Permittivity symbol will give you idea that how much times the force get decreased when you are placing the charges in different medium or increase. The force between two charges may increase or decrease when they place in different medium. That information will give you by permittivity. That is the symbol, permittivity, epsilon. So in writing formula in general, we are taking all these values in air. That's why we are writing here permittivity of a free space. Free space or air almost equal. And you can write like this formula: F is equal to K Q1 Q2 by R square. Q1 Q2 by R square. What is K? K is equals to 1 by 4 by epsilon naught. And this value is equals to, K value is always equal to 9 into 10 to the power of 9 magnitude. What are the units? K key units ENT. Now let's go through this one. How to find the units for K? I'm getting cold, that's why I'm unable to stand in front of you. Please don't mind. F is equal to K Q1 Q2 by R square. First of all, make K as a subject of the formula, then you will get a K is equals to F into R square by Q1 Q2. So here F is the subject of the formula in this, and now I just changed this. K is a subject of the formula. So this Q1 Q2 R square will come on left hand side, and it will become like this: F R square by Q1 Q2. Newton meter square by Coulomb square. Observe here, for force it is a unit is a Newton. For r distance it is in meters. Q1 Q2 Coulomb into Coulomb square. So K unit of K is Newton meter square by Coulomb square. So this is our unit for K. That I will write here. K is equal to, in free space, the value of this one. K is equal to 9 into 10 to the power of 9 Newton meter square by Coulomb square. Okay. In next class, we will discuss few more applications. Okay, prepare notes for this. Pause the video. Listen this video repeatedly. Then you will get the idea. Even you are getting doubts means you just send a voice message to me with a screenshot. Then I will explain that. Thank you.